Okay, the last thing we talked about was the different types of matters: homogeneous mixtures, heterogeneous mixtures, substances, etc. Well, now we're going to go into more detail about matter. Matter having energy. Again, the definition of matter is matter has inertia, mass, and volume. Inertia is a tendency of an object to resist any change in speed and direction. An example of that is if you rode in your car going 70 miles an hour, you did not wear a seatbelt, you got into an accident. Your body is going to continue to move at 70 miles an hour until acted on by an outside force. Usually it's going to be the windshield. So your body had inertia. All matter also has energy, and energy is the ability to do work or to transfer heat. So energy, work is equal to force times distance. So work is equal to the force needed to get it to move so far. Potential energy and kinetic energy. Okay, if you're at school or at home, whatever, you should have a textbook or a book sitting around someplace. Sit it on your desk or sit it on your bed and just look at it. It's not moving. It has potential energy at this point. It's not going anywhere, but it does have stored energy. It has potential to do something. Because if you push the book onto the floor, it's then in motion or falling, and that's kinetic energy. Energy in motion is kinetic energy. Okay, transfer of energy. Energy can be transferred either through direct contact or electromagnetic waves. If energy is transferred through direct contact, that's like kind of two things hitting each other. If you're playing pool, one billiard ball hitting the other billiard ball and causing it to go in another direction, the kinetic energy is transferred from one ball to the next. In a car crash, kinetic energy is transferred from one car to the next car, and so forth. Okay, so direct contact. Two things coming in contact, the energy from one is transferred to the other, kind of like the domino effect. Electromagnetic waves is the transfer of energy from the sun to the earth. It could also be called radiant energy. Radiant energy is energy from electromagnetic waves. It's felt as heat. Okay, energy transfer, some rules or laws. The law of conservation of mass, sometimes called the law of conservation of matter. Matter is always conserved. Matter is neither created nor destroyed. It can only change forms. We could do all kinds of examples of this. I could demonstrate this for you. We take the mass of the two objects before we do the chemical reaction. When we're done, we're going to have the same amount of mass in the end. It does not change, and I'll be doing a couple of demonstrations for you, and you'll be doing a lab demonstrating this. Then there's the law of conservation of energy. Energy is always conserved. Energy is neither created nor destroyed. It can only change forms. For example, energy is stored into coal. You burn the coal, you get heat. So it changed from potential energy into kind of that electromagnetic energy or heat. What you had to start with is what you have in the end. It's the law of conservation of matter, the law of conservation of energy. Matter nor energy can be created nor destroyed. Energy and chemical reactions. If a chemical change or chemical reaction has taken place, then you have a change in energy. In the lab you did the other day, you should have felt the sight of some test tubes, and it should have felt warm because of a chemical reaction. The magnesium strip, was it mixed with the hydrochloric acid? You should have had some bubbling taking place, and if you would have felt the side of the test tube, it would have gotten warm. So it's an example of a chemical reaction. That's kind of how it shows that a chemical reaction has taken place. The heat, it turned hot. Okay, there's a couple of one example I'll be doing where you're going to see an example of a cold, it turning cold. Heat is Q. So when we ever have problems dealing with heat, heat will be the Q. Energy transfer due to a temperature difference. So it's transfer of energy, and there's a temperature difference. Energy Heat, in other words, heat, in this case, being absorbed is known as an endothermic reaction. So if energy is being absorbed or if heat's being absorbed, you're going to have an endothermic reaction and it will be felt as being cold. The heat's kind of going in, so then the outside area is left cold. Energy, heat in this case, is being released. It's an exothermic reaction. Exothermic. The heat is exiting, the heat is going out, so you feel it, it's going to feel hot. It's going to feel hot. That should say not heat there, it should say hot underneath the word energy. All reactions need energy to start, and that's the activation energy. So the energy to get the reaction going is known as the activation energy. And I will be, like I said in class, doing a demonstration showing you endothermic reaction and an exothermic reaction. Endothermic, the heat gets sucked in, so then the outside is felt cold. Exothermic, the heat goes out, so then the outside is felt hot. Okay, we're talking about heat, hot and cold. We're talking about temperature changes. In chemistry, we usually use Celsius, but chemistry can also use the Kelvin scale. So we have the Celsius scale and the Kelvin scale. The Celsius scale, freezing is 0, boiling is 100 degrees Celsius. Kelvin, freezing is 273 degrees Kelvin, boiling is 373 degrees Kelvin. As you can see, the difference between the freezing point and boiling point of both Celsius and Kelvin is 100. It's just with Celsius we go from 0 to 100. Kelvin we go from 273 to 373. In Kelvin there is something known as absolute zero, and that is 0 Kelvin or 0 K. In Celsius, that would be a negative 273 degrees Celsius. It's the temperature where all particles stop moving. It's absolute zero. So on the Kelvin scale, the 0 is absolute 0. You go up kind of 273 degrees and you're at the freezing point, and that would be like of water, or freezing 0, 100. Boiling point 373. Now, there are two formulas on the screen that you can use for converting Kelvin to Celsius. Kelvin is equal to C plus 273. C is equal to Kelvin minus 273. You are going to have to remember those. You have to put those into your memory. Kelvin is equal to C plus 273. C is equal to K minus 273. Okay, at this point, you're going to want to pause the video and do some practice problems. You're going to be converting Celsius, or not really converting, but transferring Celsius to Kelvin, Kelvin to Celsius, and so forth. So if you pause your video, you can go ahead and do these practice problems. As always, you write down the formula. The formula should be written down on your paper. The C stands for Celsius. You need your label. Okay. When we use significant digits here, we don't look at we look at the measured number. 273 is a constant. We don't use that to figure significant digits. We're going to look at the number that was measured, and it was the 37 degrees that was actually measured. 273 is a constant. We don't look at that for our significant digits, so we needed two significant digits there. Okay, the second problem, we're trying to find Celsius, so we have to write in our formula. Celsius is equal to 77.2 K minus 273. And if you notice, we have 7, 7, and a 2. Those are all significant, so we need 3 significant digits. Oops, funny C. That should be Celsius. Okay, so Celsius is equal to K minus 273. The Celsius was the K was 77.2 Kelvin minus 273. Do that in the calculator, and I wrote the wrong label. No, that's right, because we're finding Celsius. I was right. Okay. We're trying to find Celsius. Okay, the element silver melts at 960.8 degrees Celsius and it boils at 2,212 degrees Celsius. Express this in Kelvin. Okay, so I have K. I'm trying to find K, so I take C plus 273. So K, I'm going to do the first one, which was 960.8 degrees Celsius plus 273. K is equal to, I'm going to put it in significant digits. I need 4 significant digits. Because 960.8 has 4 significant digits. Okay, I have to write down my formula. I'm still using the same formula. This time it's 2,212 plus 273. And so our K is equal to, and again, I still have 4 significant digits, it looks like. Okay, so there you can double check your math. First problem, we were trying to find Kelvin, then we were finding Celsius, and then we were finding Kelvin. If you see that I made any mistakes, please let me know. Okay, I'll go ahead and clear that. Okay, and I think I'm going to make another video all for itself for the unit of energy. So if you have any questions about Celsius versus Kelvin, please ask me. They are in your book. They are in chapter 3, though. I did not go over them in chapter 3. I was waiting for this chapter because this is when we're talking about chemical reactions, changes in temperature, and that sort of thing.